Hi, welcome back, class. In this video, we're going to look at this formula, which is the arctangent formula. Take a look at the form here of the integral. In the denominator, you have the variable u squared added to some constant. The numerator is du. Okay, so we're going to take a look at some examples, and as I go through them, I'll try to point out why this formula would be used as opposed to another. Okay, so here's a first example. Now, when you first look at it, you see this binomial in the denominator. The binomial has an exponent of 1. You might be thinking that this is logarithmic form. But what is the derivative of the denominator? The derivative of the denominator is 18x, and we do not have a multiple of 18x in the numerator. And that's because we don't have an x in the numerator. So it's not logarithmic form, which is why we're going to try to use this. Now it's important to note that u must contain the variable. So the first thing we might want to do is write these as perfect squares because that's what the formula requires. So in the formula itself, we have the constant part first, a squared. So 25 is going to be a squared, which means that a is 5. And now, in here will be u. So we have 9x squared, and its square root is 3x. So now that we've got the denominator written as two perfect squares, we can state quite easily that a is 5 and u is 3x. Okay, so because the derivative of u is 3, before we make use of this formula, we will have a factor of 1 over 3. Okay, and again, that's because du is actually 3 dx. So we're going to have a factor of 1/3, but now we can simply write out this right-hand side. So it begins 1 over a, so that's 1 over 5, and now it's the arctangent, or the tangent inverse if you prefer. And now we write u over a, so 3x over 5, and then there'll be a plus c. In the final result, we'll make the constant out front 1/15. So we get 1/15 of the arctangent of 3x over 5 plus c, just like this. Okay, let's take a look at the second one. Now again, we did questions that looked similar to this in our last lesson. And it was an example of logarithmic form, but the difference now is that these are not the same. Because if we made the bottom u, the whole expression u, the derivative of it would be 4 times e to the 4x. And this is not a multiple of e to the 4x. So that's how we know it's not logarithmic form. So what we can try to do then is what we did in the previous equation, which is to take the denominator and write the denominator such that we have two perfect squares. So 16 is the square of 4. And what about e to the 4x? What is it the square of? It is the square of e to the 2x. using laws of exponents, 2x times 2 gives us the 4x required here. Okay, so now what do we have? We have that a is 4. U will always contain the variable, so u is e to the 2x. So what is du then? It is 2 times e to the 2x. Taking a look at what we have here, we have e to the 2x dx, not 2e to the 2x dx. So we're going to need a factor of a half. So we're going to have a factor of a half, and then we go right away to our formula. So 1 over a is 1 over 4. Then we will have the arctangent of u over a, so e to the 2x over 4, and the plus c. Final answer, therefore, will be 1/8 times the arctangent of e to the 2x over 4 plus c. Just like that. So hopefully you can see that while both number 1 and number 2 looked at first glance like they might be logarithmic, okay, and that's because the variable is in the denominator and the exponent in the denominator on those binomials is a 1. They were not logarithmic because we did not have a multiple of the derivative of u in the numerator. Okay, so the derivative of the denominator could not be found in the numerator. Okay, let's try our third example now. And again, if you're thinking, well, the variable's down here, the trinomial has an exponent of 1, maybe it's logarithmic. Just think for a minute, if we called this bottom u, its derivative would be 2x plus 6. We do not have a multiple of 2x plus 6 up here. So what we're going to try to do is take this bottom thing and write it as a squared plus u squared, where a is a constant and u contains the variable. Now, how do we do this? Well, this is called completion of the square, and you would have practiced it in semester 2. Okay, but let me remind you how it goes. So we'll do it off to the side here. So what we want to do is we want to start with a perfect square trinomial. How do we create that perfect square trinomial? Well, we have x squared plus 6x. What constant should be here such that we would have a perfect square trinomial? The answer is 9. So if this were a 9, we would have the square of x plus 3. Okay, if you can't just do that by inspection, we learned a way to handle this. You start like this, then you take the 6 and you divide it by 2, and then you square it. So 6 divided by 2 is 3, and 3 squared is 9. So 9 is the desired number. But we had 13. So we've only got 9 here now. So we still have another 4 right there. Okay, now we factor this trinomial. So we have a product of 9 and a sum of 6. So those numbers are 3 and 3. So we have x plus 3 times x plus 3, which is x plus 3 all squared. Then the plus sign, and 4 we will write like this, 2 squared. So now we have each of these, this part, is a perfect square. This part is also a perfect square. Okay, so again, take the coefficient of x, divide it by 2, and square it to get this number. Figure out how much remains here, right? 13 is 9 plus 4. This trinomial will be factorable, and it'll always be the square of some binomial. And this number here, you should write also as a perfect square. Okay, so now I'm going to come over here and rewrite this. And remember, the formula goes a squared plus u squared, which means constant first. So I'm going to write 2 squared plus x plus 3 all squared. And I'm going to make note, a is 2, u is x plus 3. Now, the derivative of x plus 3 is 1, so there will be no factor out front, which means we can go right away to the formula. Okay, where is the formula? Down here. So I'm just going to do this. 1 over a, arctangent u over a plus c. 1 over a, arctangent of u over a plus c. Like that. And this is a definite integral. Okay, so now we will go ahead and simply evaluate the definite integral. So I can leave the 1/2 here. And then I'm going to do arctangent of, so first we substitute 3, and we'll get 3 plus 3, or 6 over 2. And that's 3. Minus the arctangent of, now we substitute -1. -1 plus 3 is 2. 2 over 2 is 1. Like that. And now we can put this into our calculator. So again, arctangent is the same thing as tangent inverse. So once again, you have to be in radians mode with your calculator. Okay, so we're going to do the factor of 1/2. I'm going to open up a bracket. Now we want the tangent inverse of 3. So shift tangent 3 minus the tangent inverse of 1, shift tangent 1, close it up, and there's our answer. Okay, and to 3 significant digits, this is 0.232. Okay, and that's example 3. And I'm going to do one more. Okay, so remember, we've been working on, in this lesson, how can you tell when is it this equation and when is it this equation? Right? That's what I've been highlighting in my examples. So let's look at number 4. So we begin by looking at the denominator. And the denominator is r squared plus 9. If we take the derivative of that denominator, we find that it's 2r. And that's interesting because you can see 2r here in the numerator, part of this binomial. So if the 5 were not here, then we would have a u in the denominator and exactly 2r dr, which is du in the numerator. And so we would have right away perfect logarithmic form. Okay. Now, what about if the 2r was not present and we had just the number 5 in the numerator? Then we would have essentially just the differential dr in the top because the 5 could be moved forward. So if this term were not present, then we would have just the differential dr on top of r squared plus 9. And that would be perfect for our arctangent formula. All right, so then what can we do? We can actually write this as 2 separate integrals that are being added. So for each of these integrals, we will have r squared plus 9 as the denominator. In the first integral, the numerator is 2r. In the second integral, the numerator is 5. And of course, these integrals are added because originally we have a sum. And we can do this because it follows the rules regarding the addition of fractions. And now we consider each one. And remember what we said about this one. We said, let's let u equal r squared plus 9. If we do that, then du is 2r dr. The derivative of r squared plus 9 is 2r. And so this integral becomes exactly du over u. Now, the plus sign, and let's have a look at the second integral here. Well, for this second integral, I would suggest that we move the 5 to the front, leaving only dr in the top. And then recognize that 9 is the square of 3 and write the denominator like this, 3 squared plus r squared. And now compare that integral with this form. And you can see it compares perfectly with our a equal to 3 and u is equal to r. So the first integral is just the ln of u. And the second one, after 5, we have multiplication by, and now we use 1 over a arctangent of u over a. And there will be one constant of integration at the end. So final result then, over here, of course, we have to put back r squared plus 9. And here we can make this 5/3 arctangent of r over 3 plus c. Okay? All right, so again, we split this into two different integrals. One is logarithmic, the other is the arctangent. So this example really illustrates the main difference between this form and this form. So I've selected some questions from your textbook. Please go ahead and practice with all of those problems. Okay, thanks and have a great day.